Hi, my name is Vanessa Myhaver, and this is my presentation on Resonant Trojan EMRIs with Lisa in collaboration with Dr. Jeremy Schnittman. To begin, Resonant Trojan EMRIs are multiple EMRIs in a single system locked into one-to-one resonant orbits, analogous to Jupiter's Trojan asteroid system. So in our top right-hand figure, we have the Sun in the center, Jupiter on the left, and the 5 Lagrange points. L1 through 3 are unstable, and L4 and L5 are stable Lagrange points. Within this system, L4 and L5 are symmetric, so for our positioning for our simulations, we can choose either the L4 or L5 Lagrange point. For our simulations, we'll be using the L4 Lagrange point. So in our analogous multiple Emery system, we have on the bottom right-hand corner the supermassive black hole in the center and the two stellar mass black holes in the analogous locations of Jupiter and the L4 Lagrange point. And it's these two stellar mass black holes that will be co-rotating around the supermassive black hole, locked into that one-to-one resonant orbit. And so the goal of this project is to determine whether the resonant Trojan Emery system produces gravitational waves that hold a mix of unique observational features compared to that of a single Emery system for the LISA mission. So just as an introduction for this presentation, for our simulations, for the equations of motion, we'll be using the Newtonian, first post-Newtonian, and 2.5 post-Newtonian terms. And for the gravitational wave equations, we'll be using the quadrupole expansion. And then just to outline this presentation a little bit, we'll first start out with the short-term Trojan Emery orbital dynamics. There are three types of orbital dynamic families known as the fundamental, tadpole, and horseshoe families. We'll then go into the long-term dynamics, looking at the inspiral evolution of the fundamental Trojan and single Emery systems. And then lastly, we'll look further into the tadpole dynamic family through an eccentricity analysis for the stable and resonant systems. So to begin our short-term dynamic analysis of the resonant Trojan Emery system, we first start out with the fundamental Trojan system. And so here, this is a very specific set of initial conditions that lead to the XY projection on the left here. We're in the co-rotating frame, and we will be for all of our short-term dynamics that we'll be looking at. And so in this XY projection, we have the supermassive black hole in the bottom left-hand corner and the two stellar mass black holes in the analogous locations of Jupiter and the L4 Lagrange point. And so here, these two stellar mass black holes will be, again, co-rotating around that supermassive black hole counterclockwise. But the main thing to notice within this plot is that these two stellar mass black holes reside in the locations of Jupiter and the L4 Lagrange point. And so we're actually detecting no libration of these two bodies. And this is one specific set of initial conditions that lead to this system. And so if we take that gravitational wave of this position, we get a perfect sinusoidal curve. And this actually looks analogous to a single Emery system and what we would expect from that gravitational wave. And so here in the short-term dynamics, we expect in the long-term dynamics that the fundamental Trojan and the single Emery system will look identical, but we'll get into that more later in the presentation. So just taking this a little step further, we will calculate the Fourier transform of the gravitational wave curve to get the gravitational wave amplitude plot on the bottom right-hand corner. And within this plot, we have one main peak, and this occurs at 2 times the orbital frequency of the system. And so this actually detects the motion of the two stellar mass black holes around the supermassive black hole, but we're not actually detecting any motion of the two stellar mass black holes as they do not librate from their initial analogous locations of Jupiter and the L4 Lagrange point. But then if we adjust those initial conditions, so our initial position and velocity that we're setting these stellar mass black holes at, we'll see that we can get these tadpole or oval type shape curves from our orbital dynamics. So if we look at the XY projection on the left, we again have that supermassive black hole in the bottom left-hand corner, and then our two stellar mass black holes given by the green and blue curve. And so here they're tadpoling, so there is libration of these two bodies. So then if we calculate the gravitational wave of this position, we then see that we no longer have this perfectly sinusoidal curve. And so we do see a difference between the fundamental and the tadpole orbital dynamics within our gravitational wave curve. So then again, taking that Fourier transform to get the gravitational wave amplitude plot on the bottom right-hand corner, we now have 3 main peaks, and these occur at 1, 2, and 3 times the orbital frequency from left to right. And so that center main peak represents that co-rotation around the supermassive black hole. So we're again detecting that motion, but now we have these 2 outer peaks, and this actually detects the motion of the 2 stellar mass black holes at their closest and furthest approaches from each other. So within our gravitational wave amplitude plot here, we are detecting the motion of those 2 stellar mass black holes. So we are able to recognize that there are 3 bodies within this system instead of 2, which we saw in the fundamental Trojan EMRI system on the previous slide. So then again, just adjusting our initial conditions very slightly, we now get the Horseshoe orbital Trojan EMRI system. So looking at that XY projection, we have our supermassive black hole in the center and our 2 stellar mass black holes given by the green and blue curves. And so within this XY projection, what happens is that the 2 stellar mass black holes begin at their analogous locations of Jupiter and the L4 Lagrange points, and then they horseshoe down to the bottom left-hand corner where they meet at their first closest approach, and then they horseshoe back up to the top right-hand corner where they meet at their second closest approach, and they'll continue this in more long-term dynamics, but while also co-rotating counterclockwise around that supermassive black hole. So then taking the gravitational wave of the horseshoe orbital dynamics, we get the top right-hand figure. And here we see, again, we no longer have that perfect sinusoidal curve, but we also see a different curve compared to the tadpole orbital dynamics. So in our gravitational wave plot, we are seeing a difference between the fundamental and the horseshoe orbital Trojan EMRI systems. And then again, taking this one step further, we calculate the gravitational wave amplitude, which is on the bottom right-hand corner. And we get, again, 3 main peaks here, that center peak being at 2 times the orbital frequency, that's that co-rotation around the supermassive black hole. But then we have our 2 outer peaks, and these again are at 1 and 3 times the orbital frequency, so these are at the closest and furthest approaches of the 2 stellar mass black holes in reference to one another. But one thing you'll notice here is that these 2 outer peaks are much smaller than the previous slide, and that's because the actual motion taken by the stellar mass black holes throughout each orbit is much smaller than that of the tadpole orbital dynamics. And so here, both within the gravitational wave and the gravitational wave amplitude plots, we're seeing a difference between all 3 types of systems, the fundamental, the tadpole, and the horseshoe dynamics. So we are able to detect a difference between all 3 types of dynamics, but now we want to look at more long-term effects to see if we can recognize a difference between the multiple EMRI system, so this resonant Trojan system, compared to a single EMRI system, given the same initial conditions in the long-term evolution for the LISA signals. To begin analyzing the long-term evolution of these resonant Trojan EMRI systems, we'll be constructing these gravitational wave amplitude contour plots, which basically represent the signal that we would receive from the LISA mission given these various types of systems. So to begin, we're going to be looking at the fundamental resonant Trojan EMRI system and its time frequency evolution. And so to actually construct these contour plots, what we would like to do is begin at a certain separation, for example here, say 30 RG, and then run it for an extremely long amount of time until we can actually represent that evolution. But given our equations of motions, it's extremely difficult to do that long run. It would take weeks, up to months, potentially even to run this one example that we have here. So how we construct these gravitational wave amplitude contour plots is that we start at a certain separation, say for example here it's 30 RG. We'll run for a certain amount of orbits until it reaches a second separation, say for example 29.5 RG. We'll run that certain amount of time. We'll then calculate the gravitational wave amplitude of that system, and then we'll basically turn it sideways and place it into this contour plot, into these columns that are shown in black here. And then we'll move on to the next separation. So at 29.5 RG, we'll then run it for that certain amount of orbits to get to 29 RG, and then we'll again do the same thing. And so we'll slowly stitch together these smaller runs in order to create this gravitational wave amplitude contour plot, which represents the long-term evolution of the system. So now that we've constructed this, given the fundamental resonant Trojan Emery system, so given this one specific set of initial conditions, we take these set of initial conditions and we run them for this non-eccentric single Emery system and for the fundamental resonant Trojan Emery system. And then we create these gravitational wave amplitude contour plots, which are shown here on this slide. And so here we can see that there's relatively no difference between this non-eccentric single Emery system and the fundamental resonant Trojan Emery system within these gravitational wave amplitude plots. And because of this, this actually represents the fact that the LISA mission will not be able to detect a difference within its signals from a non-eccentric single Emery system compared to the fundamental resonant Trojan Emery system. So now that we've looked at the long-term evolution of the fundamental resonant Trojan Emery system, we can move on to the tadpole orbital resonant Trojan Emery system in terms of its long-term evolution to create these gravitational wave amplitude contour plots that we did on the previous slide. And so previously, with that fundamental resonant Trojan Emery system, there's only one set of initial conditions that actually lead to that system. And so it's much easier creating these contour plots with that system because we're only setting those initial conditions at every separation. But here with the tadpole orbital resonant Trojan Emery system, there is a variety of initial conditions that can actually lead to this tadpole or oval shape that we're seeing in this XY projection on the left here. And so because of that, we have to do a bit more at each step in order to ensure that we're accurately evolving the system over time. And so here what we need to do is we need to look at the radial eccentricity, the phi eccentricity, which are both labeled on the XY projection plane, and also the semi-major axis of the system. And so here we calculate each of these values for both of the stellar mass black holes and then create an average of each of these. And using this average, we can see over time at a certain separation, so say we start off at 30 RG, we run it for a certain amount of orbits as we did previously. But here what we need to look at is that change in eccentricity and semi-major axis during that run. And then at the end of the run, we need to determine what that eccentricity and semi-major axis is and set our initial conditions to start off at the next separation in our evolution to then go on from there, set those initial conditions, and then evolve the next set of orbits to get to the next separation. So here we need to do a little bit more at each step of the process to determine what our eccentricity and semi-major axis should be at that next step in the evolution to actually create these contour plots. But there's one more step in the process that we need to follow in order to construct these gravitational wave amplitude contour plots of the tadpole orbital systems. On the previous slide, we discussed how to receive our target radial and p eccentricity at each separation in order to evolve our system naturally. But at each of these separations with that target eccentricity, we need to determine what the initial conditions are for that system in order to actually receive those radial and p eccentricities. So on this slide, we're showing contour plots of the various velocity and angle initial conditions that we release our stellar mass black holes at, and then the eccentricities that match these initial conditions. So in our process of constructing these contour plots, we start at a certain initial condition, we run for a various amount of orbits, and then we get to our next separation. At that separation, we determine our target eccentricity. We then pinpoint that target radial and p eccentricity on these contour plots, and then determine the set of initial conditions, the velocity and angle, in which we need to release these stellar mass black holes at that separation in order to evolve it naturally over time. So once we do that, we then move on to our next separation and follow this process for each of these separations to then stitch together this gravitational wave amplitude contour plot. So this is the step in the process that we're currently at, the actual construction of all of them. So we're creating all of our contour plots and determining all of our target eccentricities, and then we're going to begin to stitch all of these together. So we don't have these results at this moment, but this is the process that we're following to actually construct these tadpole orbital gravitational wave amplitude contour plots. But there's one more thing that I'd like to point out on these eccentricity contour plots on this slide. For the resonant Trojan Emery system, we must remain both stable and in resonance, meaning that the two stellar mass black holes must remain in that one-to-one orbital resonance. On these contour plots, you'll notice that the highest eccentricity shown is 0.56, and this is because any initial conditions outside of these contour plots lead to an eccentricity that is too high and then creates a system that is unstable. So here we're showing only our stable tadpole systems, and so what we also want to explore is what systems or what initial conditions lead to a resonant system as well. So anything that is not resonant does not coincide with our resonant Trojan EMRI systems that we're trying to explore. Here, there are various structures on these contour plots, so we want to look at the various eccentricities and various initial conditions and determine whether everything on these contour plots lead to both stability and resonance, or if there are different types of tadpole dynamics that we could be exploring within our gravitational wave amplitude contour plots. So for example, if we look more closely at one of the lowest eccentricities on this contour plot created by the tadpole orbital system, and then plot the dynamics created by the initial conditions that produce this eccentricity in the XY projection on the right, we see that the two stellar mass black holes remain in one-to-one orbital resonance around the supermassive black hole in the center. While they do have close and further approaches from each other, creating this oscillating pattern, over time, they remain resonant throughout the entire evolution of the system, which means that this example is in fact a resonant Trojan EMRI system, and these initial conditions are something we would like to explore in our long-term evolution, giving us the gravitational wave amplitude contour plots. But if we look closely at one of the different structures in this contour plot and plot the XY projection on the right, we see that they have a very close approach right at the beginning, and then break their resonance immediately after their close approach, making this system no longer a resonant Trojan EMRI system. So these initial conditions are not something we would like to explore in our gravitational wave amplitude plots because they do not produce a resonant Trojan EMRI system. In summary, we've identified the difference in the short-term dynamics and gravitational wave signals of the various Trojan EMRI systems. We've also determined that the least emission will not be able to identify a unique signal produced by the fundamental Emery Trojan system and a non-eccentric single Emery system with the same initial conditions. In terms of our future work, we'll continue to analyze both the tadpole and the horseshoe Trojan Emery systems for stability and resonance, and then determine whether the least emission will be able to identify unique signals produced by both the tadpole and horseshoe Trojan Emery systems compared to single Emery systems with the same initial conditions. Lastly, we'll include the octuple expansion in the gravitational wave model to determine whether this will make any difference within our LISA signals. Thank you so much for listening, and feel free to leave any questions.